Welcome to the class manufacturing process lecture 5. Today we are going to talk about continuous casting, die casting and casting defects. First start with the continuous casting. Uh, the main application of this casting is to produce continuous any casting product, that means long products continuously with different cross sections can be produced. For example, if you talk about the construction rods, the rods that's being used in the grills, and there are a lot of beams of various cross sections. Those are actually produced continuously, and after the production, the required size can be separated using the cutting tool. And this is basically a casting process that involves a melting method and then a measuring method. I'll discuss in detail that. And the cooling method, how you would cool the casting, and then finally the forming, that means cutting to the required size of the casting. And also there is the shaping involved. That means how do you want the cross section to be? Do you want it to be circular, rectangular, or elliptical, or any kind of I beam or flange type beam angle? Okay, whatever size shape you want for the cross section, you can obtain that using a die. So to discuss this continuous casting process, first we need to have the molten material, which is shown in here. The molten material is in the ladle, and the molten material is poured into a secondary holding device where you have to maintain the certain height. Okay, so that the height of the reservoir, secondary reservoir here, has to be kept always constant. That means the liquid height in this container has to be always constant, and that is maintained by the floating suisse, or sometimes the hole provided here that can also be adjusted to adjust the flow of molten material from ladle to this holding container. And there can be many different methods for controlling the height, so that the pressure below this line remains always constant. Otherwise, if the pressure is varied, then it will not be possible to get the uniform products. The properties of the output material will be different in different sections of a large beam. And once the material passes through this secondary reservoir, then it drops into a mold. Okay, and the mold has the output that we require. Like if we see the mold in here, actually, then you can see that it has a rectangular shape. The mold has a rectangular shape. So the output product will also be the rectangular shape. So sometimes you can call it as a mold, and sometimes you can also call it a die. Through this die, depending on the shape of this die, the output material's shape will be determined. That means if it is a rectangle, then the output material will be rectangle, and if it is circle, then output material cross section will be circular. So in this case, what happens is that when molten material comes from the secondary reservoir to the die, it starts to cool down, because the die have the cooling method integrated into it. This symbol actually indicates the cooling. That means there are the holes, as you see there are 6 holes in the die. Through these holes, actually, the cold water flows. Because of the flow of the cold water, the molten material, the outer surface of the molten material, that means this region, the outer surface of the molten material gets solidified very quickly. And that actually creates a shell. Okay, if we see that it is a rectangular shape. Since it is a rectangular shape, the outer surface will be solidified very quickly because of that cooling mechanism provided in there. So when the outer shell is solidified, the inner material does not need to be solidified to get it out of the die. Okay, the material gets out of the die in this way, that it has an outer solid shell and then inner there is still liquid present inside that shell. And that shell is drawn by the rollers. The rollers presented positioned in here has the rotating motion. At the same time, they provide pressure on both sides of the of the cross section, and because of the rolling action of the roller, this material continuously comes out of the die, and the material liquid metal is continuously poured into the die, and the partially solid material comes out of the die. And this material is not like very hard like room temperature material. It is still soft in the soft state but solidified, but inner surface is still in the liquid state. And in this time, this roller has another function, is that to direct the material horizontally. This whole system is in the vertical position, but because we are using the gravity system to draw the liquid from the reservoir to the die. And that is why the material, when comes out, then if you don't want to make it horizontal, it is not impossible. You apply the cooling in here and material gets solidified, and you get the long strips in the downward direction. It can go like this in the downward direction. But the problem is that if it is very long, then this whole setup has to be kept at very high. Okay, this whole setup has to be kept at very high, which is very difficult, because since you need to heat the molten material, and then the molten material requires really high temperature to melt. And after melting that material, transporting this material at a very high location will involve a lot of costs. Okay, and at the same time, there is a possibility that battery material gets solidified into the ladle before putting the material into the die. So there are some disadvantages. That is why to produce the long casting, long continuous casting, these rollers actually act as a guide to make them horizontal. The final casting gets horizontal in here, and then once the required shape is required size is obtained, this is the length of the slab, and once the required size is obtained, there is a cutting mechanism present in here. That mechanism actually cuts it off, and you have to ensure that all the material inside the core also needs to be solidified before you cut it. Okay, so that is why in these roller systems, also the cooling mechanism is applied in this roller system. That means the water is sprayed on these rollers so that the material can get solidified very quickly. And then once the material gets solidified, then the material gets out of the roller system, and then it is required size can be cut off from this location. Okay, do you have any question in here?
No, sir.
No question? Okay. And one thing I skipped in here is that since it is a reciprocating type, in the case of reciprocating type material, the die actually moves up and down. Okay, die actually moves upward and the surface gets solidified. At the same time, die gets to the downward direction. To hold the material in place, the die gets up, makes the liquid metal solidified, and then it guides the material through the rollers. Ensure the reciprocating motion is basically to ensure the proper cooling, proper solidification of the material around the slab or around the die. Okay, just to make sure that the outer shell is properly solidified before the material gets out of the die. Otherwise, if the material gets out of the die without proper solidification, so there will be distortion and the rollers will be damaged. Okay. And to visualize the material state of the material, how the material state is changing, in the ladle material is completely liquid at a very high temperature, that means greater than melting point temperature. If you say that Tm is the melting point temperature, it is very higher than the melting point temperature of the molten material metal. And then that material comes into the tarnish, where you maintain the constant height. Okay, in here we maintain the constant height, and then that comes through the entry through the entry nozzle. The material is poured into the die. Die has the reciprocating motion to ensure that the outer shell, the red region, is basically the solidified region. Okay, yeah, this is a two-dimensional representation. In three dimension, this will be all around the die. The material will be solidified. Okay. And another thing you might have noticed that the submerged entry nozzle, we are calling it like submerged entry nozzle. This nozzle is always submerged in the liquid. And there is a reason for that. The reason is that the material should not get exposed on the surface. Okay. And because if the material gets exposed on the surface, then the surface, if the proper environmental condition is not maintained in here, sometimes argon, helium, neon, those inert gases are injected in this on the top surface, so that the material does not get oxidized. That means if it is iron, then iron on the surface, because of the water present in the air, will actually interfere with the iron and produce iron oxide, which is not good for good quality material. So that might get mixed into the material, and that is why the entry nozzle is submerged into the material, molten material, so that even if there is no argon gas to protect the environment, there might a little bit of formation of oxide will form on the surface, but that will not interrupt the material. Okay, that is why the submerged entry nozzle is used. And also to provide greater protection, you might want to introduce the inert gases in this region, so that the metal does not come in contact with the oxygen or water molecule in the environment. You need to make sure that. And this is the yellow region actually shows that this is the liquid pool. That means the liquid metals remain liquid. Once the spray cooling is applied in the roller region, the material outer shell thickness gets increased and increased. At the end, the material outer shell gets completely solidified in this region. Okay, so before this place, you should not place position the torch cutoff point. That means the cutting region should not be in here. If the cutting region is in here, then the material will get out, liquid material will get out. So you need to make sure that up to which point the material remains liquid. And after that, you set up the cutoff point where when the required length is obtained on this region, then you cut it off in this region. Okay, and this is how the continuous reciprocating type casting actually works. Okay, any question here? All right. So the next one is the closed horizontal type. In this case, the system actually similar type process is kind of similar. And I forgot to mention another thing in this slide is that the amount of material you are supplying to the mold or to the die has to be calibrated in such a way that the material that is exiting from this side, material that exits from this side, the amount of material exiting from a certain position, uh, uh, and the same amount of liquid has to be placed into the mold. Otherwise, if the speed of this solid portion or speed of the solid portion is too high, speed has to be adjusted in such a way that the material, the amount of material that gets poured into here, it should not exceed. Okay, should not get out of the mold, because if the speed is slower and you put the molten material very high flow rate molten material, then molten material will get out of the system. Okay, that will create hazards. So you have to really calibrate this, that how much speed I should provide at the exit, so that I can maintain the flow rate using this height. The flow rate actually depends on the height of the material in the tarnish or the secondary reservoir. Okay. That height determines what speed you should set up to take out the material from the system. And the same thing has to be maintained in the case of horizontal continuous casting plant. In this case, the height has to be maintained properly so that the material pressure in this region is always constant. Okay. In this case, what happens is that due to the gravity of the molten material comes out of this die. Okay, and die has the cooling mechanism in here. This regions, die has the cooling mechanism. Okay, and that cooling, because of that cooling region, the die actually produces the outer shell of the material. Die actually solidifies the outer shell of the molten material that is coming out from the holding furnace or tarnish. Okay, and and the flow rate is always constant because the height in here is always constant. Okay, if the height is constant, then flow rate is constant, the material property will be uniform. And there is also secondary cooling is applied in this region uh, so that the material gets properly solidified. After solidification, this is the withdrawal unit. It's the function of this unit is that these rollers are only for supporting so that the material does not get bent. But these rollers actually pulls this thing, okay, applies the pulling force to take the solid material out so that the liquid metal can come get in. The rate at which the liquid metal gets into the cavity and the speed of this outside withdrawal unit has to be calibrated so that the if the roller the speed in here is very high, then material will get separated in here. This liquid will not cover it up. So the liquid that is coming out from the system, you have to maintain that speed. Okay. And after the required size is obtained, then you can cut it off in this region, and then the material is shifted to another location. Any question?
No, sir.
And also in the case of this die, the shape of the die can be circular, triangular, rectangular, or L shape. Whatever shape you want to obtain, you need to provide that shape into this die so that the output material will have the same shape that you want. And this is the strip casting. This is similar to that. The only difference is similar to casting, but the difference is that in this case, the output material is actually kind of rectangular strip with small thicknesses. Okay, with very small thickness. The die inside the die there is a cavity of like of this shape, and that strips coming out of the system. And if you want to apply the machining, or sometimes because of this cooling with the water or other thing that we use, because of this cooling, there are some rusting occurs on the surface of the material, and that rusting can be removed in the milling machine in here that is shown in this place, and then you roll it up. You cut it, roll it up in the up coil. When certain amount of material is rolled up, then you can cut it off in this area. Then you remove this roller and then you apply a different roller. Okay, any question? All right. There is another method for continuous casting, that is wheel belt system. Okay. Uh, it's basically a conventional type continuous casting method, but I think uh, you should know about this because you know that the technology can be sometimes very valuable. You can apply your thoughts to manufacture different things at very low cost using this kind of conventional systems. So how it works is that it has a wheel of like this. This wheel has a cavity, as you see in here. The wheel has a cavity, and the shape of the cavity can be many different types. Like if it's the shape. If I cut the wheel from this region, okay, vertically, then the the wheel has a cavity in this region. Okay, you have empty spaces, and if you use a belt on top of this wheel, if there is a belt on top of this wheel like this, then this region is treated as belt. Okay, the belt will actually cover the cavity. Okay, when you have the roller in here, this is the roller. Okay, and roller has the cavity, and on top of that there is a belt positioned on top of it. Because of that belt, uh, there is cavity is produced, empty space is produced from this region to that region. From this region to that region, there will be an empty space, which is this space is trapped by the belt. Okay, and when you pour the molten material in the open region, that means this section is open. Okay, uh, there is also cavity, but this cavity is open. But the cavity in this region is closed by the belt. Okay, and when you pour the molten material into this region, the wheel, when the wheel rotates, that material actually gets trapped like this with the belt. Material gets trapped into the blank space, and then when you apply the cooling from outside, the cooling water spray from outside, the material gets solidified from this region to that region. Okay, up to this point, the material gets solidified. Once the material gets solidified, then your solid strips you can take out the solid strips from this region. And you might wonder that the solid metal strip might strike to the other roller in here. It's not like that. It is used in the case of very small cross section on material. In that case, you can just easily bend it to skip the roller on the other side. Or you might want to use a very long distance between this roller to that roller. Okay, that is how this casting works. It's a very simple type, but sometimes for low cost manufacturing, it is very effective to produce the smaller cross sections. Like if you want to produce like a half circle, then you provide a half circular cross section in the pulley. Okay, in the wheel, or whatever section you want, you can provide it here in here. Okay, the cavity cross section will determine the cross section of the outer output material, and this is also a continuous operation. You continuously pour the molten metal, and you get continuous strips out of the wheel, and you apply the cooling on top of the belt. Okay, any question? All right. So next, to avoid the problem we saw in the first previous slide, that the molten material might the strips might get uh, strike with the other roller that is present on the other side. But to avoid that, you can change the belt arrangement like this. You can change the belt arrangement using this. This is the drag roller. Okay, and when this casting wheel actually rotates, the molten material is poured into here, and that belt actually traps the molten material inside the wheel, and then you apply cooling water in here. You apply cooling water in here, so that materials get solidified before getting out of the wheel. And then in this way, you can actually produce larger sections too, because in this case, the larger sections, there is no possibility that you don't have to bend the strip to take out. You can use the unlimited space in this region to get unlimited length of the strip you want. Okay. Okay. Any question?
Sir, I have a comment, sir.
Okay. Go ahead.
Sir, after completion, the sir one process we need a animation, sir. I think, sir, that would be better, sir.
Actually, you can have a lot of animations in YouTube. Okay? If you are interested, then you might want to check with these keywords like continuous casting, wheel belt system. Just search it. You'll get a lot of animations or real-time videos of this of all the processes I discussed in the class. Okay,
Thank you, sir.
and the crucial videos that are very necessary, I'm incorporating them in the lectures. As I have shown you a few animations. Okay,
Thank you, sir.
so the most critical thing when you need to understand, then I'll definitely show them. But everything should I cannot cover everything. Okay.
Yes, sir.
Okay, that's all for the continuous casting methods. These are the most widely used continuous casting methods for manufacturing steel or metallic products. And you might want, you can also, this technology can also be used to produce many different products. in the leather industries too. You know, if you want to produce like a belt, okay, for example, I don't know actually much about the leather engineering, but I think sometimes the resins are used, like polyester resins are used along with the fabric to produce the uh, continuous strips or shards of clothes or anything else. You can also incorporate that one. You have a cloth in here, you put the required plastic material or polystyrene on top of it, then flow it through this region, then you get the final product. The clothes will be impregnated by the liquid resins. So it's not like you use the molten metal always in this case. You can modify the systems to suit your need. Okay, whatever you need, you can just modify them. Okay, next we're going to talk about the die casting. It's very simple type. You will have a cavity, ready-made cavity on the die, and then you put molten material into that cavity with either with pressure or without pressure or just under gravity. Okay, then you get after solidification, you wait until the solidification, and then you take them out, take the material out of the die. The die casting machines are basically two types. First one is the hot chamber die casting machine. In this case, the only difference between the hot chamber and another one is the cold chamber is that in the case of hot chamber die casting machine, the holding furnace is integral to the machine. The machine and the metal melting furnace are the same machine, integral to the machine. Okay. And this hot chamber die casting machine basically used for low melting point alloys like lead, tin, zinc. These are the low melting point alloys that are used to manufacture products based on these materials. Uh, the hot chamber die casting machine is used. And there are two types. Type of enhancement can be described. One is direct air pressure type and submerged plunger type. We'll talk about both of them. Second one is the cold chamber die casting machine. In this case, the furnace that is melting the material is different. It's located in a different place than the machine. Machine is not an integral part of the machine. Is not an integral part of the casting process. Okay, casting process is located separately, and molten material is melted in a different furnace. Okay, in this case, you can almost cast many different materials and alloys, for example, aluminum, manganese, and etc. Okay. Okay, sorry, I had a call. Anyway, so for the cold chamber die casting machine, the metal is melted in a separate furnace, and we can cast almost any kind of material on the cold chamber die casting machine to produce our desired products. First one is direct air pressure type, hot chamber, direct air pressure type casting. In this case, what happens is that there is a gooseneck. That means this is called a gooseneck. It looks like the neck of duck, okay, or goose. That's why it is called the gooseneck. It is also called the gooseneck type hot chamber die casting machine. Okay, and this is the furnace, melting furnace. Burner is used to melt the molten material. The molten material will be here, and this is the gooseneck. And gooseneck will be used to transfer the molten material into the cavity. Okay, and this is the heating chamber, metal pot, and operating link. This link is used to operate the system. That means operate the gooseneck. If you want to operate the gooseneck, then you lower it and take the molten material into the gooseneck, and then you put it up. Use the air pressure to transfer the material from the gooseneck to the cavity. Okay, that means firstly you submerge the gooseneck into the molten material. Then required amount of molten, how much material you need will depend on the size volume of the cavity. Okay, depending on the volume of the cavity, you will determine how much material is required, and that same amount of molten material you put into the gooseneck by dipping the gooseneck into the molten material. After the material is placed in this region in the gooseneck, then you apply air pressure to transfer the molten material from here to the cavity Once the cavity is filled up, then cavity has actually this whole system is called a die. Okay, one part is called fixed die, and the other side, this part is called movable die. Okay, this die can be moved in in this direction, so that you can take out the casting from the system. Okay, and this die is fixed with the machine, the whole machine. Okay, so once the molten material gets into the cavity, and you apply certain time and you keep the pressure on, you apply certain time in here, so that the material gets solidified, and there will be the cooling mechanism present in the die. Okay, that is not are not shown in here, but there will be the cooling mechanism placed in the die, so that material gets cooled. Once the material gets solidified, then the movable die actually moves to the right direction, moves in this direction. Then movable die gets in this direction, and then the whole product, because of the air pressure in here, the whole material, this material will stick to the movable die. Okay, the final product will stick to the movable die. Once the die is far away from the fixed die, then ejector pin is forced in this direction to get the solidified material out of the movable die. Okay, I would like to explain this one once more, so that you get a clear concept about this hot chamber die casting machine. We have a hot chamber where the molten material is produced. Once the molten material is produced, we have an empty gooseneck. In this empty gooseneck, we take certain amount of molten material by dipping it into the molten material. We take certain amount of molten material into the gooseneck, and then we put the gooseneck in position, and then we apply air pressure, so that the molten material from here flows through the gooseneck to the cavity. When the molten material gets into the cavity, then we apply the solidification. We keep the air pressure constant, and we apply the solidification, cooling water, solidification. After solidification, the movable die will move towards the right in this direction, and the part that is produced will also stick to the movable die. Okay, and once the movable die is far away from the fixed die, then ejector pin is used to push this material out of the system. And once the dies get separated, then air pressure is also stopped. Okay, that is how this molten material hot chamber die casting machine actually works. I have a video, maybe not, not sure. Okay, this is the submerged plunger type. Okay, I don't have the video of this, but I have the other one. I'll show you that one. So the next one is that, okay, do you have any question in the previous slide? Do you have question in here? Okay, so the next is submerged plunger type hot chamber die casting machine. It is basically the system in here is same as the gooseneck type, but the only difference is that instead of using a gooseneck or dipping it into the molten material, in this case, a plunger is used to push the molten material into the cavity. Okay, and the plunger, when the plunger gets up into this position, the molten material gets into the chamber, and then when you push it like this, then the molten material trapped into the system, and that molten material gets into the cavity. And after solidification, the other method is same as the previous one. It gets the movable die gets separated, and then ejector pin is used to remove the casting from the die. Okay, this is how the cold chamber die casting method actually works. And I have a video of that, so you can see the molten material gets into the cavity. After solidification, it gets stick to the movable die, and then ejector pins are used to remove the final casting. Okay, and the plunger gets up again, and the molten material gets filled in this region, and then again when the plunger is pushed, the molten material gets into the system. Okay. Okay, this is how the system actually works for submerged plunger type die casting machine. You will have a lot of videos in YouTube if you want to see them. So in the die casting, in the case of cold chamber die casting machine, the material is the molten material is obtained in a different region, and you take the molten material and put it in the system in here. There is a cylinder where you put the molten material in this region, and then using the plunger, you push the molten material into the cavity. You push the molten material into the cavity. Once the material is into the cavity, you keep the pressure on, and then once the material gets solidified, using that plunger, you again push it so that the movable die gets separated. Then you take back the plunger, and the ejector pins are used to remove the solidified material from the system, and the material is ready for the next shot. Okay. Any question? Are you there actually? How many of you are here? Bishwajit, are you there?
जी सर जी सर
Ahsan Habib, roll number 16.
Yes, sir.
Maimuna Wadud Mim.
Yes, sir.
So if you are there, then why don't you talk? Nobody talks. That's weird. Anyway. So this is the cold chamber die casting machine and animation. Just have a look. Put the molten material into the system using the plunger, you push it there, then you push it, and then ejector pins are used to remove the final casting. It's a very simple process. And then, yeah, and another thing is that you need to always before pushing the molten material into the system, you need to use the lubrication to facilitate the removal of the casting. Final product, if you want to remove the final product very easily, then you have to apply the lubrication on the mold every time before putting the molten material into the system. There are some advantages of die casting machine. Very small amount of floor space is required. Precision less machining is required in the final product. Thin sections can also be obtained. Surface finish is good. Rejected parts are very small. High production rate. And disadvantages include cost of die and equipment is very high. Initial cost is really high because manufacturing a die is very difficult. and it requires a lot of machining operation to manufacture a die. So it is one of the disadvantages. Life of the die decreases rapidly due to high temperature. Since the machine operates at very high temperature, the die life is also very small. And only non-ferrous alloys are cast. Ferrous alloys casting is very difficult because it requires very high temperature, and controlling is not that easy. It produces different type of internal defects. That is why it is avoided. And size is limited. The large size, you cannot produce large size in the die casting because it requires a lot of molten material, and transferring those huge amount of molten material is also a difficulty. And especially skill required for die maintenance. Die maintenance is very important. If the die surface is not properly finished, then your final product will not be finished. If there is a small defect on the die, that will create a huge problem in the castings. Okay, so you need to really take care of all those things. Casting defects are basically classified into three different types. One is major or severe defect, intermediate defect, and minor defect. And the major defects are those defects which are basically irreparable. That means you cannot repair that and use that product. The product must be rejected. You cannot reuse that product. That means you cannot do a small machining and then use the product. It is not possible. Those defects are called the major defects. And the intermediate defects, the defects that can be the material, the product can be used, but in the with a little bit of modification or a little bit of machining that might require for intermediate defects. And the minor defects are very you might need just to finish the product, and it can be used as a daily product. Okay, so it is not basically a rejected product. And intermediate defects sometimes can be repairable, and parts can be used. And severe defect, you cannot use that part, that is completely rejected. So I'll talk about a few defects, casting defects that are usually seen in the case of casting. First one is the surface roughness. The surface can be very rough, not this one actually. The cause due to too coarse molding sand or high pouring temperature. Okay. The molding sand is very coarse. That means large particles are used for casting. Then the surface roughness will occur. At the same time, if in the case of die casting, if the surface is not properly polished, then you might have the surface roughness. Okay. And sometimes when the high pouring temperature, pouring of molten metal occurs at very high temperature, and that actually oxidizes the surface of the material. The final casting surface gets oxidized, and that creates a very reacts with silica to form the rough compound in the case of sand casting. And in the case of other casting, this high pouring temperature might cause surface roughness because of the reaction with the oxygen and formation of scale on the surface. Once you remove that scale, then you will get a very rough surface. And second one is the scab and buckles due to sand sharing from the cove surface. Sometimes in the die cast, in the sand casting, this type of scabs are seen. These are called scabs or buckles. These scabs are basically due to the sharing of sand. Sand gets loosened and mixes with the metal. When the sand gets mixed with the metal, they actually forms this kind of defects. The material gets very rough. These are not basically surface roughness, and scabs or buckles are not basically very severe type of defect. This can be repaired. These are repairable defect. That means intermediate defect. Next one is the blowhole. Blowhole is the internal voids as a result of excessive gaseous material. If the casting produces, the mold actually produces excessive amount of gas that may be caused because of the hard ramming. If ramming is very hard, then gases cannot escape through the mold. That means the permeability of the mold gets decreased, and that in that case, the internal voids are produced in the molten material. And then excessive moisture also one of the reason, and low permeability, improper venting. If the venting is not properly given, then the gases cannot escape. and the ingredients that are used in the scent that can also cause this kind of blowholes. This is one of the region, the example of the blowholes. If the material gases from the molten metal cannot escape, they actually produce this kind of holes in the casting, final casting. Okay, and this to avoid this, you have to have the proper permeability, and you have to really take care of the ramming. If ramming is very high, then gases cannot escape. Okay, and gas gets trapped into the molten material, and then they creates this kind of voids into the molten material. And another type of defect similar to the blowholes, but this defect is surface defect. Surface reaction cause surface porosity or pinholes. Sometimes on the surface of the casting product, they produces these small tiny holes. Okay, these tiny holes are created because of the reaction. Magnesium or some material actually reacts with water vapor to form H2, and this H2 gets trapped on the surface. Okay, and then because of that H2 or sometimes hydrogen sulfide, when sulfur is present in the metal, this kind of small pinholes are produced. Okay, and how to avoid this kind of pinholes? You need to have proper permeability, and also you need to maintain the moisture content. And in the case of magnesium casting, in the sand casting technique, using sand casting technique, you need to really take care of the sands. In the case of, we don't want to use the green sand mold that contains moisture in the sand. Okay, you have to avoid that. So this is the way you can reduce this sort of defects. So internal blowholes are severe defects. You cannot actually repair them. The material has to be rejected. But in the case of pinholes, this is an intermediate defect, can be repaired. Another one is hot tear. Hot tear occurs basically when cracks during solidification. When the material gets solidified, it has a larger section and a smaller section connected, and this connection regions actually produces cracks like this. Okay, because of the mismatch of cooling during solidification. This material takes larger time for solidification, and this takes a small time for solidification. And that is why this thin sections actually gets solidified very quickly. And that is why there is a stress difference between the solid section and the between the solid section and the partially solid section. And that is why there is crack actually appears because of the stress difference, load difference between this solidification difference between thin and thick sections. Okay. And caused by discontinuity of the casting, that means the larger or smaller sections are connected together. Excessive mold hardness, sometimes the mold is very hard and the material cannot move after solidification. And because of the restricted movement, the materials gets cracked. Sometimes the temperature is also one of the reason for molten material. If the material temperature is very high, that also causes this kind of tearing because of the material improper mismatch of the stresses between thin and thick sections. So how to avoid this hot tear? You need to really take care of the molten pouring temperature and the mold hardness, so that and also one of the important thing is that when you design the casting, you need to really take care of this, that you need to avoid having the large and small sections together. You might want to prepare them separately and then weld them together, okay, to avoid this kind of defects like hot tear. And another one is the cold shot. Two metal stream meeting together are too cold to fuse properly. That means like you are pouring the molten material through this in this way and using two different pouring line or two different gates. Sometimes multiple gates are used for large castings. So through this gate, material gets in, and also material gets in from this gate. The two material actually meets together at some point, like this. And in this case, the material is by the time material reaches this location, both of the stream actually gets become cold. That means partially solidified. And once they are partially solidified, then they cannot fuse together. They cannot become the continuous. They actually create a defect in this region. That means the material from this stream and material from this stream are not fused together. So in this case, you need to really take care of the gating. Like you might want to provide another gate in this region so that the material gets in this way too. So there will be 3 streams and they get quickly fused. Okay. So the slow pouring is another region. The material, you are pouring the molten material very slowly and the material gets solidified before before meeting each other. For gate design, that means you put a gate in here, you put a gate in another gate in here, then the material does not get fused together. So you need to really take care of the gate design. That means where you should introduce those gates so that material does not get solidified before completely reaching the whole cavity. Okay. Some other defects are also present. The fin and run out, almost similar type of defect to this run out and fin. You might, if you look at some plastic products, the low quality plastic products, you will see this kind of defects. And also for metals, these defects are there. So these defects are basically the drag and cope, where the drag and cope meets. This is called the parting line. From this parting line, if this is a casting in here, you have a casting in here, the molten material actually gets out through these regions. Okay, molten material gets out through this parting line, and they creates this kind of runouts. Okay, if runouts are very small in size, they are treated as fins. Can be also fins, and sometimes if you have a vent in there with a large diameter, then molten material can get into those vent. Okay, and then in that case there will be like fins present on the top of the surface. These are very minor defects. This can be easily removed by just finishing operation with the grinder. Okay. And internal air pockets and misrun caused by pouring boiling metals. If you have a boiling metal, it's poured into the cavity, then there will be internal air pockets, which is very similar to this defect actually. Internal air pockets are very similar to these defects, the blowholes. Okay. Because the formation of those is basically due to the boiling metals. Because of the boiling metal, the gases produced cannot be escaped from the system. And there is the misran. Misran is basically the material is too cold to reach the whole cavity. The material has not reached in this region. There is no material in this region, and the whole system gets solidified. Sometimes it can be like less amount of material is poured into the cavity. Sometimes the low pouring temperature can also cause this kind of defect. Lack of fluidity of the metal does not flow properly. That means the highly viscous metal, liquid metal is used. The material does not have enough time to reach the whole cavity. Instead, they get solidified before reaching the final, the whole region where you need to do the casting. So this is how the misram actually works. Okay, there are many other defects also resulting from improper ramming, slow feeding. These are the basic reasons for the casting defects that might occur. Metal contraction and gas generation. These are the major reasons for producing casting defects. So there are also some more defects present, which are given in the Rajendra Singh, the book of Rajendra Singh, or you can also get it from the book of R.K. Jain. You might want to also have a look at them, all other casting defects, so that you might get a broad insight about the casting defects. Okay, that's all for today. And in the next lecture, we'll be talking about welding, and hopefully you get prepared. And also I hope that you will really concentrate on the class and you listen to me and also ask questions. If you don't ask questions, then it is very difficult to continue the class. It is like I'm talking to myself. Okay, so please respond in the class so that class can be interactive, and